Good afternoon, everyone. Welcome to QSI seminar this week. And our speaker today is Xin Hong, who is a PhD student at QSI, supervised by Minsheng and Shanjiang. And today he is going to talk about his recent work on equivalence checking of quantum circuits. And before we start, I just want to remind you, during the talk, if you have any questions, please just unmute yourself and ask the speaker directly. Okay, so Xin, please take your floor.
Yeah. Okay. Thank you, Professor Feng, and thanks everyone. And today, I want to introduce this work, tensor network-based decision diagram for representation of quantum circuits to you. And the tensor decision diagram is a data structure that can be used to represent quantum circuits. And you know that an QB quantum state can be represented by 2 to the n by 2 to the n unitary matrix. And the problem of this representation is that the number of elements grows exponentially with number of qubits. And thus, it will bring difficulties for tasks such as equivalence checking and simulation and other tasks. And thus, we need to introduce a more compact representation. And binary decision diagrams provides parts of the solutions. And but the binary decision diagram is designed for the Boolean function. And thus it cannot be used directly in quantum circuit cases. But the observation is that quantum circuits can be represented by a tensor network, and thus it brings us to the tensor decision diagram. And then in the classical cases, a classical circuit is represented by a Boolean function. And I think at that time they will face the same problem that the number of elements of its truth table grows exponentially with number of variables of these Boolean functions. And I think as a solution, they provided the binary decision diagram. In the binary decision diagram, the value of the Boolean function can be obtained through a path of this graph. And at first, the binary decision diagram is a tree-like decision diagram, and every node represents a variable of this Boolean function, and it has two successors, the 0 successor and the 1 successor. Here we use the dotted line to represent the 0 successor and the 39 to represent the 1 successor. You can see that for this Boolean function, when x2 takes value 1, then this Boolean function will be 1, represented by the 1 successor. And if the value of x2 takes value 0, then the value of the Boolean function will depend on the value of variables x1, x3, and x4 represented by this 0 successor here. You can see that for this Boolean function, when x2 takes value 0, and when x1, x3, x4 will takes value 1, then this Boolean function will take value 1, and it will take value 0 in other cases. I'm
sorry. Can I ask a question?
Yeah.
So why, when x2 equals 1, the whole function is 1? Like, what's the other one?
This is a logic wall operation. Yeah.
Yeah. Oh, okay.
Yeah.
Got it. Yeah. Thanks.
Yeah. And then this here is the logic and here is the logical wall. So
plus is all, right?
Yeah. And then in the Boolean function, plus is all. Yeah. So when x2 takes value 1, the next Boolean function will be just take value 1.
Yeah, sure. Thanks.
Yeah. Okay. So you can see that this binary decision diagram can takes all the information of this Boolean function. And then this binary decision diagram can be reduced to what we call a reduced binary decision diagram in such a form. And you can see that here when x2 takes value 1, then it is also direct to the value 1 here. And if x2 takes value 0, then only when x1, x3, x4 will takes value 1, then it will be 1. Otherwise, it will take value 0. Then you can see that this binary decision diagram also captures all the information of this Boolean function. And this is a reduced binary decision diagram of this Boolean function, and it consists of only 6 nodes here. And so you can see that it can save a lot of memory spaces compared to its truth table, which have 16 items. And the theoretical basis of this binary decision diagram representation is the Gaussian expansion. That is, a Boolean function can be divided into 2 parts according to the value of a variable of this Boolean function. Okay, then following I will come to the quantum part. And you will know that a qubit can be represented by a 2-dimensional vector, and an n-qubit quantum state can be represented by a 2 to the n-dimensional vector. And then this vector can also be divided into 2 parts, I think. You can divide it into 2 parts according to the value of the first qubit. And then for every part, you can further divide it into 2 parts according to the value of the second qubit. And then for the quantum gates, every element is corresponding to an assignment of both the input and the output value of the corresponding qubit. And here you can see that this one is corresponding to cat 0 bra 1, which takes 1 as input and 0 as output. So if you assign the input of this qubit, then this matrix can be divided into the left and right 2 parts. And if you assign the output of this qubit, then this matrix can be divided into the top and bottom 2 parts. And for this single gate, 2 qubit gate, if you assign the input value of the first qubit, then it can be divided into the left and the right 2 parts. And if you further assign the output value of the first qubit, then it can be divided into the top and bottom 2 parts, and then it is just a 2 by 2 matrix. And then if you assign the input and output value of this of the second qubit, you can obtain an element of this matrix. And following, I will try to give a more specific explanation from the perspective of tensors. A tensor is a multidimensional line map, and the vectors and matrix are simply examples of the tensors. A tensor can be corresponding to a set of indices, and the number of indices is called the rank of the tensor. And here, quantum states and unitary quantum gates can just be seen as examples of tensors. And for example, for this polyzeta matrix, it can be seen as rank 2 tensors with 2 indices x and y. And for these tensors, phi x, y, its value will be phi x, y, 0, 0 equals 1, and phi 1, 1 equals -1, and phi 1, phi 0 1 equals 0 and phi 1 0 equals 0. And then a tensor can also be decomposed by a Gaussian expansion. That is, a tensor can be divided into two. What we call here is the subtensor. Here we call it 0 subtensor and 1 subtensor. And then a tensor can be divided into 0 subtensor and 1 subtensor according to the value of an index. And here, for example, if you if x takes value 0, then the 0 subtensor will be rank 1 tensor with only one index y, and phi y 0 will be 1, and phi y 1 will be 0. And if x takes value 1, then it will also be a rank 1 tensor with only one index phi y, and phi y 0 equals 0, and phi y 1 equals -1. Okay, and you can also divide it according to the index y, but now not much difference. Yeah. And then the most important operations of the tensors is called construction. And that is to sum up over the shared index. And for example, for these two tensors here, phi xy and psi yz, the construction of these two tensors will be rank 2 tensor psi xj. And cos xj equals to the summation over y phi xy times psi yz. And you can see that if phi and psi are two matrices, then the construction is exactly the matrix multiplication. And then quantum circuits and a set of tensors can be connected to form a tensor network. And quantum circuits can be seen as a special class of tensor networks. Here we use the index x0 as Wallace places, since that the T matrix is a diagonal matrix. And thus, if these two index takes different values, then this tensor must be take value 0. So there's no need to introduce different index for these places. So we just we'll use x0 here, and this forms what we call the hyperedge here. And then here are two examples of the construction. For example, you can see that if these are two hard gate, and then they will be constructed of an index y, then you can see that if x and z will takes value 0, then you can say it's just the multiplication of when z takes value 0, it corresponding to the first row of this matrix, and when x takes value 0, it corresponds to the first column of this matrix. And then when xz will takes value 0, the summation of y will be the multiplication of the first row of this matrix and first column of this matrix, and thus forms the matrix, the first item of the result matrix. And as you can see that when cos xz is exactly the multiplication of these two matrices. And if this is a hyperedge and Wallace indices are equal, then the construction of these two tensor will be there will be no summation here, since that the index x will be appeared in the result tensor. So you can see that here cos 0 0 will just equal to phi 0 0 times psi 0 0, and then it will be 1. And QSI 11 will equals to phi 11 and times psi 11, which also equals to 1. And you can see that it represents identity matrix. Since that when these two index take different values, then this tensor will be 0. So this is just what we know that two polyzeta matrix can be cancelled to form identity matrix. And there's also another example that synod gate can be divided into the construction of two tensors. Here, a synod gate can be divided into a copy tensor and exclusive OR tensor. Now here for this copy tensor, and the three indices are all labeled with x, and it means that for this tensor, when x takes value 0, 0, 0, and 1, 1, 1, and then this tensor should be 1. Otherwise, it will be 0. And for the exclusive OR, when x takes value takes value 0, you can see that x0 and x1 must be equal to make this tensor non-zero. And if x takes value 1, then x0 and y0 and y1 must be different to make this tensor non-zero. And this is what run the x gate did here to change the input 0 to output 1 and transform the input 1 to the output 0. Okay. In following, I will turn to the tensor decision diagram. Tensor decision diagram is just designed to represent the tensors. And in this representation, a tensor is represented by a node labeled with an index of this tensor, and two successors represent the two subtensors. And for the subtensors can be here we use the dotted line to represent the 0 subtensor and the solid line to represent the 1 subtensor. And the subtensor can be further divided until you reach the values of the tensors of the tensor. And here you can see that this is a tensor decision diagram representation of the circuit here. You can see that when, here when x0 takes value 0, then this x gate will not be operative, and then these two Hanma gate will be cancelled, and then and the second qubit is just equals to an identity matrix. So you can see here that when x0 takes value 0, then y0 when x0 takes value 0, y0 takes value 0, then y3 must be 0 to make it a non-zero amplitude. And if x0 takes value 0, y0 takes value 1, then y3 must take value 1. And here you can see that if x1 takes value 1, then there will be an amplitude I on first qubit. And then this x gate will be applied, and to Hadamard gate will make it a polyzeta matrix. And then you can see here when x0 takes value 1, and y0 takes value 0, y3 must take value 0, and there will be amplitude I. And if x0 takes value 1, and then y0 y0 takes value 1, and then y3 must take value 1, and then there will be an amplitude minus I. And here you can see that this tensor decision diagram really captures all the information of this quantum circuit here. And in TDD representation, we will store the values of the tensor to the edge to the width of the edges. Since that, this gives us an opportunity to merge the nodes that represent the tensor that differ only by a coefficient. And this width will be moved upwards to ensure that every node represents what we call norm tensor. That is, it is either 0 or the first value that has the biggest norm will be exactly in will be exactly the value 1. So here you can see that for this subtensor, the first value with the biggest norm 1 is I. So this I should be moved upward moved upward to here, and then for these two edges, and they will have the norm 1. Then I must be moved to here, and these two edges should be divided by I. So finally, it formed such a tensor decision diagram, and this is called a normalized tensor decision diagram. Here, this is important since that you can just multiply here by 2 and multiply here by 1/2, and then you can see that these two tensor decision diagrams will represent the same tensor, but they are different. So this will be not suitable for tasks such as equivalence checking. And thus, we have to ensure that this width must obey some rule that is normalized in here. And then the nodes like the binary decision diagram, the nodes that represent the same subunion functions should be merged, and in TDD, the nodes that represent the same subtensors should also be merged. Here first, all the terminal nodes will be merged to one neighbor with index neighbor with 1, and then terminal node 0 will be and 0 just will be moved to the width of the corresponding edges. And then the nodes that represent the same tensor, for example, here these two Y-sun node will represent the rank 1 tensor phi Y3, and phi Y3 0 equals 1, and phi Y3 1 equals 0. So these two nodes should be merged, and then the edges that direct to this node should be redirected to the node here. And this is the same for these two nodes, and then you can see that these two nodes are merged, and these two nodes are merged to this one. And then finally, the tensor decision diagram can be reduced to such a tensor decision diagram, and this is called a reduced tensor decision diagram. And you can see that it also represents the circuit here. You can see that when x0 takes value 0, then y0 takes value 0, y3 must take value 0, and y0 takes value 1, y3 must take value 1, which equals to our identity matrix. And if x0 takes value 0, there will be amplitude I on first qubit, and for the y0 and y3 here, if y0 takes value 0, y3 must take value 0, and if y0 takes value 1, y3 must take value 1, and there will be amplitude -1 here. So you can see that this node just represent a tensor that corresponding to the polyzeta matrix, and this node here just represent the tensor corresponding to the identity matrix. So you can see that this tensor decision diagram really captures all the information of this quantum circuit. Okay. Then not only the tensors can be represented by the tensor decision diagram. The operations of tensors can also be directly operated on tensor decision diagrams. For example, the addition of the two tensors. According to the Gaussian expansion, the addition of two tensors can be achieved by the addition of now one successor and the addition of now zero successors. And then in the tensor decision diagram representation, it can be achieved by the addition of now zero successors and the addition of now one successors. And the addition of now zero successors can be further divided into the addition of now zero successors and now one successors. And thus, the whole algorithm can be achieved in a recursive way, and finding the complexity of this algorithm will be the multiplication of the number of nodes of these two tensor decision diagrams. Another important operation of the tensor decision diagram is the construction. The construction can also be directly operated on tensor decision diagrams. For two tensors, here I just use this symbol to represent the construction. And here this plus is the just the plus of tensors. Here the construction of two tensors. Here the construction can be divided into two cases. First, if X is an index that should not be summed up, here you can see that the X will be appeared on result, and then the construction of these two tensors can be achieved by the construction of one subtensor of phi and psi, and the construction of zero subtensor of phi and psi. And then in the tensor decision diagram representation, it can be achieved by a load neighbor with index X with two successors represent two results of construction here. The construction of its zero successor and psi, and the construction of its one successor and psi. And then another case is that X is an index that should be summed up. Then the index X will not be appeared in the result. Then this can be achieved by the construction of now zero subtensors plus the construction of now one subtensors. And here in the tensor decision diagram representation, it can be achieved by the construction of now zero successor and the construction of now one successor. And then these two results should be added. And this is just the addition of the tensor decision diagram we introduced before. You can see that the construction of this two successors gives TDD, and the construction of these two successors give a lot of TDD, and then these two tensor decision diagrams can be added, and then they will form the tensor decision diagram of the final result. And then the complexity of the construction is the square of the multiplication of the nodes of these two tensor decision diagrams. And then with these two operations, and then you can obtain a tensor decision diagram of quantum circuit through just first you generate the tensor decision diagram of every single quantum gate, and then you construct them more, and then finally you can obtain the tensor decision diagram representation of the whole circuit. Okay. One property of the tensor decision diagram is that the canonicity. That is, the tensor decision diagram representation of a tensor is unique. More specifically, if F and G are two reduced tensor decision diagrams that represent the same tensor and use the same index order, then these two tensor decision diagrams must be isomorphic. Thus, you can see that for these two circuits, and they will have the same tensor decision diagram as this one. Then, according to this zero, and then you can see that these two circuits are equivalent. And the advantages of the tensor decision diagram is that it is compact. It can compress the memory spaces needed to store a tensor, and it is very flexible and can be combined with all kinds of optimization techniques of tensor networks. Following, I will introduce some applications of the tensor decision diagrams. Tensor decision diagrams can be used to do the simulation and the equivalence checking of the quantum circuits, and it can also be used to compute the trace of quantum circuits and many other aspects. Here is an example we find out when we calculate the tensor decision diagram representation of the circuits of Yuan used the benchmark called the Ravenip. And there is a circuit called the QFT10, which is Yuan used as the 10 qubit quantum Fourier transform. But it turns out that this circuit does nothing, and it just equals to the identity matrix. When we calculate its tensor decision diagram representation, then we find out that the state one node now, and its tensor decision diagram is as this form, and it's really represent the identity matrix. So it is totally not the quantum Fourier transfer circuit. And another application of tensor decision diagram is to calculate the trace of quantum circuit, and this is what we use in approximate equivalence checking. For matrix, the trace of a matrix can be calculated through such tensor network. That is to collect its input and output, and then the construction of this tensor network will just get the trace of this matrix. And for a quantum circuit, you should to collect the input and the output of every qubit. And then the construction of this tensor network will give the trace of the corresponding unitary matrix of this circuit. Following, I will mainly focus on approximate equivalence checking. First, quantum circuits can be seen as a set of quantum gates, and here is 2 qubit quantum Fourier transform. And then the noisy quantum circuits can be seen as a set of noisy quantum gates. And noisy quantum gate can be represented by a superoperator, or it can also be represented by a set of cross operators. And then for density matrix, though, transformation over superoperator can be in this form, that is summation of ni zero ni diagram. Now here gives an example of the depolarization channel. It consists of 4 cross operators: the square root of p I, the square root of 1 minus p over 3x, and the square root of 1 minus p over 3y, and the square root of 1 minus p over 3 zeta. And then the quantum circuit and the noisy quantum circuit itself can be represented by a superoperator, and its operation elements can be the composition of the cross operators of one is noisy gates. And the ideal gates itself can also be seen as a superoperator with only one operation element. And then the approximate equivalence checking is to check if 2 noisy quantum circuits are close enough. That is, their fidelity are bigger than a certain value. More specifically, that epsilon be a value in 0 to 1, and C1 and C2 be 2 noisy quantum circuits represented by superoperator E1 and E2. Then these 2 circuits, C1 and C2, are said to be epsilon equivalent if their fidelity is bigger than 1 minus epsilon. Here the fidelity we use here is the Jankowski fidelity. And then the problem of the approximate equivalence checking is to determine given an epsilon and determine if 2 circuits are epsilon equivalent. And here we consider the case that when one of the circuit is the ideal circuit. This is the real case we need it in realistic. Since that we want to check if a noisy quantum circuit is close enough to its ideal version. And first, the fidelity of 2 density operators rho and sigma on hyperspace is defined to be the square of the trace of the square root of rho 1 over 2 sigma rho 1 over 2. And then the fidelity of density operators can be transformed to the fidelity of 2 superoperators by using the Jankowski isomorphism. The Jankowski isomorphism maps a superoperator to corresponding density operators. Here, for superoperator E, the corresponding density operator can be obtained by I tensor E operated on the maximum entanglement state. And then the Jankowski fidelity of 2 superoperators can be defined to be the fidelity of the corresponding density matrix obtained by using the Jankowski isomorphism. Okay. Here we use the Jankowski fidelity, since that the Jankowski fidelity can serve as average case error, and it is stable. That is, an extended system will not influence the equivalence of the original system. and it obeys the chaining rule. That is the distance between two circuits will not be, and the error between two circuits will not be accumulated too quickly if there are too many noisy gates. And more importantly, the geometrical scale fidelity can be calculated easily. Here, if E is a supervector and U is unitary matrix, here they represent a noisy quantum circuit and corresponding ideal quantum circuit respectively. And then the geometrical scale fidelity of this two circuits can just be calculated through such a form. Here is the here EI is the operation elements of the supervector, and U is just the unitary matrix. D is just the dimension of the corresponding Hilbert space, and then what we really need to calculate is this term, that is the summation of the square norm of trace U dagger EI. And then we propose the two algorithms to calculate this term. The first one we calculate one term trace U dagger EI every time. And for this one, this term can be calculated through such a tensor network. Here, U dagger can be achieved by the inverse of the original circuit. Here, you represent the ideal circuit, and it can be achieved by the inverse of the original circuit. And the EI is just cross operator of the corresponding noisy quantum circuit. And then this and EI is just a cross operator of the corresponding noisy quantum circuit. It can be obtained by the composition of the corresponding cross operators of wireless noisy quantum gates. And then for every EI, you can construct such a tensor network, and then you can get the value of such a term. And then you construct the tensor network for all of the EI, and then you can get wireless terms, and then you calculate the norms, and then you add up their squares. And then finally you can obtain the value we needed. The advantage of this algorithm is that the tensor network we need to construct is small and can be calculated efficiently. But the problem is that the number of elements should be constructed grows exponentially with the number of noisy gates. And thus, when the number of noises are too large, it will be not suitable. And thus, we provided the second algorithm. In the second algorithm, we calculate this term at one time. And in fact, this term can be calculated by constructing such a tensor network. And here, every qubits are doubled, and every quantum gate here will have a conjugated copy in a corresponding copy qubit. But for the noisy quantum circuit, it will be represented by its corresponding matrix representation, and finally constructing such a tensor network will give the this term at one time. And for this algorithm, the advantage is that no matter how many noisy quantum circuits, no matter how many noisy gates now, you just need to construct one tensor network. So when a lot of noisy gates, it should be efficient. But if there are just a little noisy gate, then this tensor network will be too complicated compared to the algorithm one. We implemented our two algorithms using the Tensor Decision Diagram package, and the experiments are conducted on some commonly used algorithms, and for example, the quantum Fourier transform and Bernstein Vazzirani algorithm and quantum volume circuit. And we compared our results with the QSI package. And here is the number of qubits of the corresponding circuit, and G is the number of quantum gates in the corresponding circuit, and K is the number of noises we inserted into the corresponding circuit. And you can see here that when number of qubits are big, in fact, it's not very big. When the number of qubits is relatively big, then the QSI will consume a lot of time. And if the number of qubits are bigger than 7, then the QSI package will out of memory. But for all these circuits, our two algorithms will not will never out of memory using the Tensor Decision Diagram representation. And you can also see that when the number of noises are small, then the algorithm 2 consumes more time than the algorithm 1. But when the number of noises are big, then the algorithm 1 will consume more time than algorithm 2. And you can see that from this circuit, the algorithm 1 is just out of time. That is, it consumes more than 30,600 seconds. We also conduct experiment to compare the performance of our two algorithms, and this experiment also shows that when the number of number of noises are small, algorithm 1 will outperform the algorithm 2. But if the number of noises are if there are too many number of noises, then the algorithm 2 will outperform the algorithm 1. Okay. In concluding, the Tensor Decision Diagrams has both the advantages of the decision diagrams and the tensor networks. It can save the memory spaces to store the information of the tensor, and it can it can be operated flexibly, combined with all kinds of optimization techniques of tensor networks. And in the future, we will complete and optimize the TD package and try to find out more applications of the Tensor Decision Diagrams. And in fact, at present, our TD package is still not very efficient. So we need to do a lot of improvement here. Okay, I think that's all about my talk today. Thanks for listening, and please say if you have any questions.
Yeah, and thanks, Hongxin. Very nice talk. So let's take some questions from the audience.
Hello. So I knew nothing about this field, but I have a naive question, which is so this is about the representation of quantum circuits, and what are the is there any other representations of quantum circuits? So
yeah,
I mean, just like
there are
examples, like just a few names is okay. Yeah, just you don't need to explain. What? Yeah.
I think just for decision diagrams, there are two representations called the quantum information decision diagram and quantum value decision diagram. They all have different characters. At present, the quantum information decision diagram is not very used, but the quantum mathematical decision diagram is used in many cases. And I think the tensor decision diagram have its own advantages over these two decision diagrams. That is, for the quantum mathematical decision diagram and the quantum information decision diagram, they will represent for example, if you want to represent a single qubit gate, but for these two decision diagrams, they have to represent it on all of the qubits. But for tensor decision diagram, you just need to represent it using the corresponding index. So I think this is an advantage. And I think that for tasks such as here, for example, the noisy gates, it will not be very suitably represented by the quantum value decision diagram or quantum information decision diagram. And for tasks such as the trace calculating, I think the tensor decision diagram will also work better than these two decision diagrams. Okay, I think that is the case.
Right. Yeah. So I guess your representation is not the first. That is like not the one that we are used to. So comparing to other, like the ones that I haven't seen, what's the position of the of your representation among all the others, like the ecosystem, like if there is such thing, is it like?
Sorry, I didn't get your question.
Yeah, I was just curious. Is there, so how many say, is there a number of the representations that exist? I mean, by other researchers, like how many are there? Say, like, is it 10 or 6 or is there too many, or is just a few?
You say how many? What? You saying the number of nodes or?
No, I'm saying the types of representations of quantum circuits that exist today, like proposed by not only you but previous researchers, like.
Yeah.
Because I googled this like representation of quantum circuits, and the results. First of all, this seems not a textbook material that everybody knows. So I guess I'm asking here, I mean, maybe I'm wasting time, but this is, I mean, might be useful for my research in the future. So I just want to know, yeah, about this field, like what are the other representations that are important to represent quantum circuits?
Oh, so you can see that you can just represent quantum circuit as unitary matrix, but for example, if you want to calculate the unitary matrix of a quantum circuit, it will be you have to store an exponential number of elements on your local computer. But if you use such tensor decision diagrams or quantum information decision diagrams or quantum value decision diagrams, and one is representations can help you to save the memory spaces. Thus, you can cope with the quantum circuits with more qubits in your local computer. And otherwise, if you just use the matrix representation, you will always face the problem of auto memory. Yeah, I think that's the case.
Yeah. Okay. Perhaps I'll give you an example that I've seen. It's called quantum multiple value decision diagrams.
Yeah. Quantum value decision diagrams.
So I guess my question is this kind of thing, is this the quantum multiple value decision diagrams another type of representation of quantum circuits, which is like parallel to yours? It's just another type. Let's say you are competitors for some.
Quantum value decision diagram is around a representation of a quantum circuit. I think they will have same characters, that is to save the memory spaces, but they will have different characters. The features of the tensor decision diagram is that it uses the ideas of tensor networks, but the quantum mathematical decision diagrams just represent it as represent every single qubit gate has an n-qubit quantum gate, and it can do the multiplication of it can do matrix multiplication. And for tensor decision diagrams, it just represents a tensor and it can do the tensor construction. So they are same in some aspects, but they will have different features and suitable for different tasks. Yeah.
Okay. Yeah, thank you. Thank you very much.
Okay, so any other questions? So Hongxin, may I have a question?
Yeah.
So, if I understand correctly, the normalization and the reduction of the TDT representation is very time consuming. So obviously it's not optimal to do such kind of tasks very often, right? So do you have any general techniques or heuristics on how and when to do such kind of things during the computation?
Yeah. I think here I just should separately. I just should the normalization and reduction separately to tell you what the main idea here and what is it used for. But in fact, in the real calculation process, we first generate we generate the tensor decision diagram we generated are wall radius, and then when when next to, for example, when for next algorithms, when we calculate the two tensor decision diagrams, and in next step, it will face normalizing and reducing. And then here we will maintain that these two subtensors, then the subutilities are all reduced, and then so you just in this step you just need to do the normalizing and reducing for these two edges, and in fact, the normalizing and reducing can be did in at the meantime, and it will not be there is no need to eternity to reach one node below these two edges. Yeah, I think that is the case.
Okay, I see. So is there any other questions?
If there's time, can I have one more?
Yeah.
In my impression, so this kind of like representation is the application or the advantages that helps with the calculations, right? Say the simulation and so on. But I'm more concerned of can this kind of representation captures the symmetries of the, first of all, of the quantum circuit itself, and then of the input data. Say, if the input of your quantum circuit has the data have some symmetries, and would these representations be able to capture and take advantage of the symmetries in the data?
I think that I think that if for example two unitary matrix have two, if it's just a symmetry matrix, then these two sub matrix should have if it's just symmetry. Maybe so I think it's if for unitary matrix, if these two matrix are just equal, then they will be represented using the first node in the tensor decision diagram. Then you can see that from this tensor decision diagram, you can find out if this matrix have such character. But if that's just symmetry, I think maybe it maybe cannot be read out from just the structures of the tensor decision diagram.
Right.
Yeah.
Okay, thank you. I guess I'll, yeah, thanks.
Any other questions? So if there's no more questions, let's thank the speaker again. And also thanks everyone for coming today, and hope to see you guys again in next seminar.